Performance of high-density concrete with iron ores and alumino thermit portion. As a radioactive barrier. High-density concrete is widely used in railway, crane counterweight, radiation shielding in nuclear plants or other radiation-related application and medical establishment. The aim of this study is to increase the density of concrete and accomplish it by using iron ores, obtain form iron quarries as aggregates and thermite portion. The traditional concrete aggregates were replaced by iron ores aggregates in amount of 100%. Physical and mechanical properties, density CS, TS, freeze-thaw resistance were determined. The aggregates of concrete plays an essential role in modifying concrete properties and physical-mechanical properties of concrete. On its shielding properties, the attenuation measurement will perform by using gamma spectrometer scintillation detector, of NaL, and finds shielding factors, HVL half-value layer, TVL 10th value layer, as well as attenuation coefficient. Keywords: iron ores, radioactive barrier, concrete shielding, tomography, structure XD. 1. Introduction. High-density concrete consists of concrete with density higher than normal, i.e. 2,300 kg per cubic meter to 2,550 kg per cubic meter. HDC is used for special purposes such as radiation shielding, counterweights, safe walls, safe roofs, and trading cost for space saving. Concrete is most widely used material for reactor shielding due to its cheapness and satisfactory mechanical properties. The aggregates components of concrete that contains mixture of many heavy metal, like free iron, plays an important role in improving concrete shielding properties. The density of heavyweight concrete is based on the properties of component and the SG of aggregates. High-density concrete is a concrete having density in the range of 6,000 to 6,400 kg per cubic meter, is also known as heavyweight concrete. Due to better shielding, it protect from harmful radiation like X-rays, rays, neutrons. Concrete with respect to specific gravity higher than 2,600 kg per cubic meter are called heavyweight concrete, and high-density aggregates with respect to SG higher than 3,000 kg per cubic meter are called heavyweight aggregates. SG is the ratio of the density of substance to the density of reference substance, or it is the ratio of mass of substance to the mass of reference substance for the same given volume. Local hematite stone were used as aggregates to produce HDC for application in X and gamma shielding concrete cube sample, 150-150-150, containing hematite as a coarse aggregate prepared by changing mix ratio, with C ratio and types of fine aggregate. The concrete specimen of size 100-100-100 also will form to pass maximum radiation through own self with reference to distance, inverse square law. 2. Methodology. I. Material used. Aggregates. High-density concrete, HDC, is achieved by using high-density aggregates, usually iron oxides. The most important part of HDC aggregates is that the grading should be constant and that a workable grading limit be agreed on with the supplier. The chemical properties of all high-density aggregates should be evaluated before use in high alkaline environments as found in cement pastes, long-term durability such as alkali aggregate resistivity, sulfate and chloride attack, and other impurities. The cost of HDC increases with density but not necessary in direct proportion. Aggregates should be selected for their shape free of flat or elongated, maximum density, workability, and cast. The grading of the coarse aggregate should be uniformly graded between 10 mm and 20 mm as grade 1 and 4.75 mm and 10 mm as grade 2. Natural aggregate. Different parts of natural high-density aggregates which can be used for high-density concrete, HDC, as iron ores. Man-made aggregate. To achieve concrete densities above 6,000 kg per cubic meter, man-made of synthetic material such as ferrosilane slag, steel, or lead shot can be used. Overall HDC are used barite, ferrophospho, Rus, limonite, hematite, ilmenite, magnetite, geotite, steel punching, steel shots. 1. Cements. If alkali reactive constituents are present in the aggregate, cements with low alkali contents or a suitable not having more than 0.6 and Na20 may be used with a potentially alkali reactive aggregate such as lead shot. When lead shot is used, high alumina cement, HAC, must be used as it reduces the chemical reactivity of lead in high alkaline condition. Deleterious expansion can be prevented by using alkali reactive aggregate, lead shot, and high alkali cements with adding extenders. Bulk density, kg/m3, 1200. 2. Admixtures. Superplasticizers are beneficial in reducing water to minimize bleeding and maintain a cohesive mix that has minimum segregation. Water reducing admixtures, as it will increase concrete density by reducing the amount of water. Water is the material used in HDC with the lowest density. Shrinkage reducing admixtures, as it ensure dense, crack-free concrete used for radiation shielding concrete. One of the widely used superplasticizers has a Na20 of about 5% and if added at 1% of Ce meant to the concrete. Lithium-based compounds can be used with lead shot to control the alkali reactivity. Property of concrete/aggregate. 1. Neutron shielding property. Example: radiation shielding concrete. The shielding properties of this concrete against is being used to build bunkers, mazes, and doors in medical accelerator. The objective was to characterize the material behavior against neutrons, as test alternative mixings including boron compounds in an effort to improve neutron shielding efficiency. The original mix, which includes a high fraction magnetite, was then modified by adding different proportion of anhydrous borax, Na2B407. Properties of high-density aggregates and concrete. Ferrophosphorus density, kg/m3-4080-5290. Steel punchings or shot density, kg/m3, 4650-6090. 2. Sample casting. Mixing, curing, testing of specimen. The material were placed in the mixer with capacity of 56 dm3 in the following sequence. 1. Material were initially dry mixed for 2 minutes. 2. Approximately 80% of the mixing water was added and there the mixer was started. 3. After 1.5 minutes of mixing, the rest of the mixing water was added to the running mixer in a gradual manner. 4. All batches were mixed for a total time of 5 minutes. 5. In order to prevent fresh concrete from segregation, the mixing duration was kept as low as possible. 6. All concrete 3 specimens were cast in 3 layers into 150 x 150 x 150 mm cubic steel molds, each layer consolidated using a vibrating table. 7. After casting, concrete specimens were covered with plastic membrane to avoid water evaporation and thereafter kept in the laboratory for 24 hours at ambient temperature. 8. After demolding, concrete specimens were submerged into water tank until the time of testing. Quality control. Production, placing, compaction. Standard batching procedures can be used for naturally occurring aggregates such as barytes and magnetite to allow for the increase in aggregates' relative density. It is sometimes necessary to use smaller drum mixers approximately 0.5 cubic meters and smaller, for lead shot. Normal batching and handling equipment can be used, but great care should be taken not to overload the equipment as HDC is much denser. Batching times will take longer per cubic meter. But individual batch mixing times should be similar to those for standards aggregates. The slump for high-density aggregates mixtures should normally be between 40 and 75 mm. It is far more susceptible to variations in quality due to improper handling. Concrete should be placed in layers not more than 30 mm thick. The concrete should be free of segregation and voids. Higher frequencies vibration causes segregation of high-density aggregates by settlement. I.e. large aggregate migrate to the bottom to the element. The area radius of accretion of vibrators used in HDC is less effective. 3. Sample testing. Radiographic evaluation of concrete. A. Radiations, rays, characteristic. Gamma rays. 1 wavelength, short, 0.005 angstroms, to 0.5 A0. 2 frequency more than 1019 Hz. 3 velocity v of light, 3.108 m/s. 4 penetration, can even pass through 30 cm thick. 5 deflection, iron no affect electric and magnetic field because of no charge or mass. 6 energy, high energy M radiation, energy greater than 100 keV. B. Principle of radiographic testing. It is based on the principle that radiation is observed and scattered as it passed through an object. If there are variations in thickness or density in an object, more or less radiation passes through and affects the film. Exposure flaws shows up on the film. C. Shielding property. Radiations, A, SS particles can be blocked by sheet of aluminum. Rays require several inches of lead, concrete, or steel to be stopped. Lead shielding. It reduces the intensity of radiation depending on the thickness. This is an experimental reaction with gradually diminishing effect as equal slices of shielding material are added. A quantity known as having thickness is used to calculate this. Having thickness of lead is 1 cm, which means the intensity of gamma radiation will reduce by 50% by passing through 1 cm of lead. Concrete shielding. It can be used to shield against both neutrons and rays. It is composed of a mixture of cement, 13%, water, 7%, aggregates, 80%. OPC is referred to as light and has density of about 2.2 to 2.4 g/cm3. Heavy concerts have densities ranging from about 3 to 6 g/cm3. Ferrophosphorus or aggregate and limonite mixture have been used because of their greater densities and higher water content. The barium sulfate or aggregate, baryte, is also used to form heavy concrete. These concrete contain boron for neutron absorption and hydrogen for neutron attenuation. The barite ore is also a good gamma attenuator. The thermal neutron absorption properties of concrete can be greatly enhanced by the addition of boron compound. Hydrogen in fixed water, hydrated, from and free water, in the pores, in concrete serves as a good neutron shield. Initially the free water content is about 3% by Wt. The water may be lost at ambient temperature by evaporation. To minimize evaporative loss, design criteria limit of ambient temp, is 149 degree, for photons shield, 71 degrees Celsius, for neutron shield, max internal temperature for photons shield is 171 degrees Celsius and 88 degrees Celsius for neutron shield. 3. Radiographic examination and measurement. Examination with projector and substance. I. Projector use Sentinel 880 Delta, other Elite, Omega. The patented device body consists of a titanium S-tube and cast-depleted uranium, DU, shield contained within 300 series stainless steel tube with stainless steel discs welded at each end forming a cylinder-shaped housing. The discs are recessed to provide protection for the rear-mounted outlet part. It radiographic, rays, inspect to materials and structure in the density range of about 2.71 G/cm3 to 8.53 G/cm3. Specimen tomography. It is application of gamma rays transmission in studies of water vertical ascending infiltration sample of concrete. NDT, ultrasonic pulse velocity, pulse echo, radioactive tests, radar test, acoustic emission but are used to determine the defects of concrete. In tomography after a number of profile of narrow beam transmission are obtained at different orientations around a sample such measurement total linear attenuation coefficient of rays along the path of the ray. Let if n corresponding number of photons existing the sample then exp4. Monoenergetic ray beam. Linear attenuation coefficient. At